okay? Always talking about y values. Down below, going to use three phrases alternatively, okay? Going to use three phrases alternatively. Those words are going to be absolute, global, and max and min. If I say, guys, what is the maximum? I want the highest point. If I say, guys, what's the absolute max? I want the highest point. If I say, guys, what's the global max? Highest point. So I can either leave the word global and absolute out, in which case if I just say maximum, I'm referring to the absolute or the global, okay? So when I say max, global max, absolute max, these are all referring to the same thing. Okay? These are all synonymous for one another. Now, what this definition says, right? And you know, when you look at the definition, guys, invariably it looks confusing, right? But here's what it says. It says to have an absolute global maximum or minimum, this has to be true. I have to have a y value that's great. So we'll use this one first. Okay. What does that say? To have a maximum, I have to have some y value that's greater than or equal to every other function's value. That makes sense, right? To have a maximum, I have to have a y value that is greater than or equal to every other value of the function. To have a minimum, I have to have a y value that is less than or equal to every other value of the function. Seems reasonable, right? So here I give you this graph, okay? I want to know, first of all, what is A? What is the value of A right here? It's a minimum, right? So what could I call this value? I could call it a minimum, I could call it a global min, or a absolute min, okay? So what I'm going to use, guys, is I'm going to say f of A. What's nice about that, guys, is it not only gives me the position, but it also tells me the x value where it happens, right? So f of A is a minimum. All right, what would be the maximum here? F of D. So f of D is a maximum. All right, and again, I could use different phrases. I could use global or absolute for both of those, right? So far, no problem, right? So what I'm going to do with these 6 examples is I'm going to sketch them, and then we're going to talk about what happens with these, because some weird things are going to happen when we sketch these. First of all, what is the first graph? It's a parabola that's been shifted up 1 unit, right? So this would be a picture of my entire graph, correct? But I don't want the entire graph. I only want the portion of it between -1 and 2. And I'm going to highlight that in yellow. That's that portion of the graph, right? And I want to identify maxes and mins. So is there a high point? Again, I'm only looking, guys, at this yellow portion of the graph. Is there a point that is higher than all other points? F of 2. Is there a point that is lower than every other point? F of 0. And so that seems reasonable, right? That seems reasonable. Now watch how our conversation changes on this next one. Same graph. What's the difference? Instead of having filled in circles at -1 and 2, I'm going to have what? I'm going to have open circles at -1 and at 2. And I'm going to have the graph that is in between. Now, before you answer the question, I want you to think back to the limits. Okay? Is there a high point to this graph? Is there a high point to the graph? Well, somebody might say it's at 1.99, right? Because why can't I say 2? It's not part of the what? It's not part of the interval, right? So maybe Michaela says it's at 1.99, Ricardo. And then maybe Elizabeth says, no, it's at 1.999. And then Weeks goes, well, it's at 1.999 repeating. Can I ever get to the maximum? Can't ever get there, right? Because invariably, forever and ever and ever, I could always do what? Get closer and closer and closer and higher and higher and higher, right? So in terms of a max, there is no max. A maximum does not exist. I can't be at a maximum where there's a hole, can I? Okay. Is there a minimum? Yeah, it's at 0 still. All right. Well, that's the next one. Well, the next one I have what? I have the same graph, except I have a hole at 0. Same graph, except I have a hole at 0. And I have a closed interval that starts at -1 and ends at 2. But then I also have what, guys? I also have a point that I need to plot at 0, 2. So I also have this point up here. Does that seem okay? All right, so is there a high point to this curve? Yeah, it's up here, right? Is this point well defined? It is, right? So there's a max at f of 2. Is there a minimum? No, why not? Because what's at the minimum? The hole, right? At the minimum value is the hole, and I can't ever get to that thing. I can keep getting closer and closer to it, which means I keep going lower and lower. So the minimum does not exist. So far, if you were to make a conjecture, your conjecture would be what? A max or a min can't happen at a hole, right? A max or min can't happen at a hole, okay? Let's see, part D. Same graph. -1 and -2, still closed. -1, -2, still closed. And a hole here, but a point that is plotted at 0, 0, right? So again, what does this mean? It means give me the graph except at 0, then plot something at 0, 0 on this interval. High point? F of 2. Is there a point that is defined as a low point lower than all others? Yeah, right here, right? That point is lower than all others. So the min is f of 0. All right. What am I going to do here, guys? I'm going to graph a sine curve, right? Now it says graph a sine curve from 0 to 4 pi. So how many cycles do I graph? 2 cycles. Very good. And we know that each cycle tops out at 1, bottoms out at -1. And since I'm drawing a sine curve, right? Where's the sine curve start? At 0, yeah. So it starts at 0, up to 1, back, down to -1, back. There's 1 cycle of sine. But then I have a second cycle of sine, right? Boom. Now this brings in the definition, right? This brings in the definition because I was really, really clear about that definition. What did I say? I said a maximum occurs when the graph is at or equal to all other points, right? Is there a point that is higher than or equal to all other points? Yeah, right here and right here. So there can be two values where a maximum occurs. Okay, if they're what? If they're at the same level, right? If they're at the exact same position. So I have maxes. Okay, guys, what's this value? Pi over 2. What's this one? This one right here is 3 pi over 2. 5 pi over 2. Very good. And then Vanessa, I'm going to have a minimum at 3 pi over 2 and 7 pi over 2. Very good. Yeah. So for our purposes, guys, you're never going to have to do that, right? There'll be a limited domain. You're thinking about like the NPi thing that you did in calculus. Yeah, we won't do that, but you're right. You could have an infinite number of maxes or mins. 2 minus 3x, guys, what's that? That's just going to be the graph of a line. Going to look something like -1, 5. And look kind of like this guy. Their max. F of -1, min 2. Seem reasonable? All right. And again, this is where you really have to know your definition, right? Because this next example, oh wait, where is it? Why isn't it on here? Oh, it's right here. Sorry. Okay. And then I want to graph 3 from 2 to 4. Or -2 to 4, sorry. So do you guys agree that that's this picture right here? Right? Okay, so again, this is, do you really understand your definition, right? What did I say the definition was? You're at a max if you're at a point that is higher than or equal to all other points. So ready? This point right here. Is it higher than or equal to all other points? How about this point right here? Is it higher than or equal to all other points? Yeah. So isn't it true that I'm at a max anywhere between -2 and 4? But it's kind of weird because what's the definition for a min? To be at a min, I have to be at a point that is lower than or equal to all other points. Is this point lower than or equal to all other points? Yeah. So guess what? The max and the min are the same, right? The max and the min are the same. So the max and the min are going to be, I'm going to write this kind of weird, okay? Is going to be 3. That's an upside down A. An upside down A in math is going to be called for all. So it's going to be 3 for all x values that are between -2 and 4. The maximum is 3 for all x values that are an element of the interval -2 to 4, right? And you've seen this written before, right? X is an element of -2 to 4. You haven't seen the upside down A. So that means for all values within this interval. So far, so good? The 3 is where it happens, right? Like over here, I said f of -1, f of 2. Here, I can't really do that, right? Yeah. So it's just 3. All right, and so the extreme value theorem. Here's what the extreme value theorem says. This brings us to, there's going to be a couple of value theorems. Okay, there's going to be a mean value theorem that we're going to talk about. Now we're going to talk about the extreme value theorem. So here's what it says. It says that if I have a closed interval and a continuous function, both of those are important. Continuous, closed. If I have a continuous function and a closed interval, then I must have a max and a min. Okay? Guarantees. Guarantees, 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 guarantees. Has to. Now, guys, if I have a non-continuous function and a non-closed interval, it doesn't mean I don't have a max or min. It just doesn't guarantee that I have one. Cool? Okay. So, in this picture right here, continuous. Closed? Closed ends? Do I have a max and a min? Max, min. Continuous. Closed endpoints? Max, min. Continuous. Closed endpoints. Maxes, mins. Fair to say? Let's look at a bunch of cases that don't have those things. Okay? What's wrong with the first one? Discontinuous, right? Discontinuous. Now, right? So if I asked you, does the extreme value theorem apply in this case? You say no, because f of x is discontinuous at x equals 1. Now, again, does that mean that I can't have a max or min? No, I still might have one. It just doesn't guarantee that I do. Okay? So is there a max to this one? No. What's it? Because what's wrong with it? What's at the top? A hole. So there is no max. Is there a min? Is there a point lower than all others? Yeah, where is it? F of 2. Good. Guys, if I asked you what the minimum is, you would either say f of 2 or you would say 0. Because what did I say at the very, very beginning? When I'm talking about extreme values, I'm always referring to y's. Okay. Next example. Does it apply? Does not. Why not? It's not a closed interval. It's also what? It's also discontinuous, right? Okay, so we'll just say not a closed interval. Not a closed interval. Is there a min? Why not? There's a hole. Is there a max? No. What's my graph going to do? It's going to keep going up, 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 right? So what could I say the max is? I could say it's infinity, or I could say it does not exist, right? It can't get to infinity, so it doesn't exist. Does it apply? Why? Discontinuous. Is there a high point? What is it? Is there a low point? What is it? 0. So again, here we see what? We see that the extreme value theorem did not apply. However, there was still a max and min. Last one. Does it apply? Because it's what? Not a closed interval. Is there a max? Yeah, I can't really say, oh, actually I can say what it is. What is it? 3. Is there a min? Yeah, do I really know what it is? No, it's f of 1.5-ish, right? We'll just pretend. We'll just pretend it's at f of 1.5. So I guess the other one's at f of 0.5 then, if you wanted to do that. Guys are liking this so far, right? I hope so. I hope you're liking it so far. All right, so now we know when, right, we're going to have a max and a min. The next question that we have to decide is, how can we do this algebraically, right? Because looking at the graph, no problem, right? But how can we do some of this algebraically? Guys, this phrase right here is going to be important. I'm going to use it all year. The phrase is going to be critical value. Okay? Really, really important phrase. Here's what you need to know about critical values. Critical values occur in one of two scenarios, where a derivative equals 0, where a derivative does not exist. Hey guys, we took a test and I asked you about critical values. I just didn't use the phrase. One of the things I said, where does this graph have a horizontal tangent? A horizontal tangent is where a derivative equals 0. Or I said, where does this graph have a vertical tangent? A vertical tangent is where a derivative does not exist. So we've already talked about this. I just haven't used that phrase, critical value. When we come back, we will finish this up. So before our break there, in my 25 minutes online, or on the phone, what we said was that we could find critical values. Critical values happen when derivatives equal 0 or don't exist. Okay, so we've already done all that. Now you're going to figure out why, right? Why? So, when we talk about absolute extrema, right? So we've already used this phrase absolute, right? They can only happen, guys. These things can only happen at critical values or at endpoints. Make a note of that. Extrema can only happen at critical values or endpoints. Extrema can only happen at critical values and at endpoints. Guys, we saw that on these graphs, right? Where did the extremes happen? At the endpoints, right? Or at the critical values. Now, what do I mean by a critical value? Well, critical value is where derivative equals 0 or doesn't exist. Guys, right here. What's the derivative at a cusp? Doesn't exist. Guys, what's the derivative at a turning point? 0. What's this? This is an endpoint, right? Endpoint. Endpoint. Does the derivative exist here? Why doesn't it not exist? Because for a derivative to exist, the derivative from the right and the left has to be the same, yeah. So we're seeing some of these things happening, okay? Now, new phrase, relative and local. Relative and local. Think back to your pre-calc class. Extrema don't have to necessarily be absolute. In other words, I can have higher points or lower points on a graph. We're going to talk more about what that means in a minute. And make a note of this. Relative extrema can only occur at a critical value on an open interval. And we'll see that happen in a second. But make one more note down here, this one right here. Local extrema cannot happen at an endpoint. Local extrema cannot happen at an endpoint. And that was always a point of confusion. And I'll talk more about that as we look at the next example. So here I have a graph. What I want to know is what's happening at A, B, C, D, E, and F. Okay? What is happening at A, B, C, D, E, and F? So I have F of A, F of B, F of C, F of D, and F of F. And I want to classify these as either endpoints, critical values, maxes or mins, absolute or local. We're going to use lots of different phrases. So look at f of a. Talk to me about f of a. It would be a absolute minimum. Okay. Why is it not? Actually, let me try to actually write that in English. Why can't that be a local min? Because you can't have local mins at endpoints. Okay, the beginning and the end can't happen. Okay. F of b. What's f of b going to give me? It's going to give me a local maximum. Why is that a local maximum? And here's the test I want you guys to think about. Guys, if you look a little bit to the left, are the points higher or lower? If you look a little bit to the right, are the points higher or lower? Lower. If the answer to both of those was lower, then f of b had to have been a local max. Okay? Yes. Oh, we're gonna see that in the next example. By the way, guys, talk to me about the derivative right here. What would be the derivative at this point? 0. Yeah, so let's make a note of that. The derivative would equal 0. Okay. So would it be a critical value then? Yeah, because we said critical values happen when derivatives equal 0 or don't exist. Okay. What about f of c? Go to f of c. Go a little bit to the left, and where am I? Above or below? Above. Go a little bit to the right, and where am I? Above. So what does that mean? C had to have been a local min. And what do we know about the derivative at a cusp? It does not exist. So what does that mean? Critical value, right? By the way, this would also be a critical value, wouldn't it? Because what did I say were critical values? Critical values where the derivative equals 0, the derivative did not exist, or was an endpoint, right? So make a note of that. This was an endpoint. F of D. Talk to me about f of D. Maximum. Maximum. If I wanted to add the word global or absolute, I could, right? But this is an absolute max, and the derivative equals 0 there, right? How about f of e? I know. All right. Yep. Okay. What about f of which one am I on? E. What's E, guys? Local min. Derivative equals 0. What about f of f? Nothing. F of f is nothing. It is a critical value because it's a what? It's an endpoint. So it's an endpoint, but it takes on none of those properties. It can't be a local min, it can't be a local max. Could it be an absolute? Can endpoints be absolute? Yeah, endpoints can be absolute, just not what? Just not local. Okay. All right, so that's pretty straightforward, right? Now I give you this. Not as straightforward. Not as straightforward. Okay. I'm going to look at all these different values as we go through this. So I'm going to look at f of -4, f of -3, f of 1, I'm sorry, f of -1, f of 1, f of 2, f of 4, and there's one more we're going to add to this as we go. All right, so talk to me about f of -1. What's happening at -1? I have a closed endpoint, right? Is it the lowest value or the highest value? Yeah, f of -4. Yep, f of negative, what did I say? Oh, sorry, f of negative 4. Definitely going to be a what? Absolute min. Definitely going to be an absolute min. Is it a critical value? Yes, because it's a what? It's an endpoint. All right, let's go to negative 3. What's happening at negative 3? Well, I'm at this point when I'm at negative 3, correct? Look a little bit to the left of it, and where am I? A little bit to the left of it puts me right here, doesn't it? Look a little bit to the right of it, puts me right here, right? What are both of those values? Below it. So what does that mean f of negative 3 had to have been? A local max. Talk to me about the derivative. What would be the derivative at negative 3? Does not exist. Can't have a derivative at a whole, can you? Okay. Go to negative 1. Go to negative 1. It's an endpoint. But, okay, so when I say endpoint, I'm talking about endpoint of the entire graph. Closed interval, so the whole graph. So it's not an endpoint of the whole graph. Do you agree? When I say the endpoint of the whole graph, I mean this whole thing that I'm looking at. And this right here, right? Begins at negative 4, ends at 4. So that's the endpoints that I'm referring to when I say that. So as soon as I get there, I want you to look a little bit to the left, and where am I? Below. A little bit to the right, and where am I? Above. What does that mean? It's nothing. It's nothing. F of, or actually these are H, these are H's. Here, just change this to be an F so that it looks better. Okay, now this one's kind of interesting, guys. I got to add something to this list. Don't you guys agree that there are values all the way in here which I can discuss? What are the derivatives anywhere along this? 0, right? Because what's the slope of a horizontal line? 0, right? So wouldn't it be fair to say, if I pick any point on here, there's no point higher and there's no point lower? Kind of like that example of 3 earlier, right? So what I'm going to say is this. I'm going to say I have an absolute max. Because that's definitely going to be the highest points on my curve, right? No doubt about it. I have an absolute max of 2 for all x values between negative 1 and 1. Is that cool? Right? And again, why is that true? Because the derivative was 0. All within that range. Critical values, right? Guys, what else is true though? Is there a point between negative 1 and 1 that is lower than any of these? Now I said between negative 1 and 1, not including negative 1 and 1. Yeah, it's a local minimum, isn't it? Because there is nothing that is lower than any of this. So it's an absolute maximum and it's a local minimum. When I, yes. So when I say, again, the thing that you want to be careful with when I say a closed interval and local mins and maxes, I'm not going to include either of those in terms of the endpoints. Okay, so hang on. So you're thinking of the extreme value theorem. Closed interval and continuous. Okay, but remember, extreme value theorem what? Guarantees that I have an absolute min and a max, right? It doesn't necessarily mean that I don't have one if I don't have a closed interval. See the difference? Okay. So I have a local min 2 for all x values between -1 and 1. So that's a little weird, right? It's a little strange, but there it is. How about at 1? What's going on at 1? Well, I'm all the way here, aren't I? So if I go a little bit to the left of 1, where am I? Up there, right? If I go a little bit to the right of 1, where am I? Up there. So what is 1? A local min. And that would be because the derivative does not exist at that value. How about a 2? Play the left-right game, guys. Local min, because if you go to the left, you go up. If you go to the right, you go up. See it, Artie? No? Okay, so if I go, you agree this is the point right here, right? So if I go a little bit to the left of that point, I go up. If I go a little bit to the right of that point, I go up, right? So don't you agree that that point is lower than the 2 points to the left and to the right? So that's a local min then. And again, the derivative there would not exist, right? And lastly, how about at 4? How about at 4, guys? None. Why not? It's an open endpoint, and this is not higher than everything else, so it can't be a local max. It's nothing. All right, so when we look at this graphically, guys, especially an example like this, it can be a little bit confusing, right? And so I'm going to show you how we're now going to tackle this algebraically. Okay, and now we're going to do some work with the derivatives that we did before, okay? Except they're going to be really, really easy, really easy. So what does this say? It says find the domain and find the critical values. So as soon as I say let's deal with the, oh, hang on, before we do that, domain. Guys, what is this the graph of? It's a power function, or I'm sorry, it's a polynomial with a 4th degree, right? So it's a quartic, okay? Is there any holes in this graph? Are there any asymptotes in this graph? Is there anything to restrict the domain? No, there's no radicals. It's not a sine or a cosine function. So if I have one of these guys, I'm pretty confident that the domain, all reals. All right, critical values. How do I have critical values? I have critical values when I take my derivative. All right, well, what's the derivative of a half of x to the 4th? 2x cubed minus 3x squared minus 2x. And what do I want to know about this thing? First of all, is there any values where this doesn't exist? No, the only time that's ever going to happen is if I have a radical or a fraction, right? So the only critical values are going to happen when the derivative equals 0. Agreed? All right, what am I going to do? I'm going to factor out an x. That's going to give me a 2x, x, 2, 1, minus, plus. So I have critical values at 0, -1/2, and 2. And this is the aha moment. Everybody be ready to say aha. Aha. Ready? Ready for the aha moment? Okay, here's the aha moment. Back when you did polynomials last year, and you got one of these, and you were asked to graph it. Well, maybe you did this. Maybe you found some roots. Agreed? Maybe you found some roots. So you would set this equal to 0 and you found roots. Agreed? Okay. And then maybe you looked at that and you plotted the y-intercept. And maybe you looked at this and we said it. It's a quartic, which means the end behavior is one of these, right? So right now, this is what you know. You know that this graph has a y-intercept of 2 and does that, correct? But you also know this. It was going to be so good. No. Those are the turning points of your graph. We'll come back to that. That's where it's heading.